We are in Module 2, Atoms and Molecules. We get to start talking about stuff as opposed to just concepts. Now, this is different from the second edition and earlier. This is the part where I said that in the second edition and earlier, they actually start, I believe it's the second or third module, is thermodynamics and using equations for heat transfer. This module is set up with a little bit different teaching methodology, one that I think it makes more sense for the first student in chemistry, in that we start talking about the pieces, the stuff, the building blocks. And we go through a period of talking about the building blocks, and then later we advance to what those building blocks do in terms of transferring energy and changing form and all that kind of thing. So you kind of benefit from the module, or excuse me, from the third edition. First and second edition were structured a little bit differently. And there's debate between which is better, but I still think that this is a positive for you to do it in a slightly different order. So where does all this fit? Well, we start talking about matter by talking about philosophy. So philosophers in here, this is cool for you, right? Socrates, Plato, Aristotle, and Alexander. Names hopefully you're somewhat familiar with. Socrates, and they schooled each other. They're kind of a lineage, if you will, or a heritage. A lot of people know about Socrates, Plato, and Aristotle. Not many people understand that Alexander the Great was mentored by Aristotle, who was mentored by Plato, who was mentored by Socrates. So these huge thinkers in Western philosophy, and we tend to think of Alexander the Great not as a philosopher, but mostly for his world domination, you know, conqueror of the known world, the Hellenization of the world through Alexander the Great. So our understanding of matter actually comes from this philosophical bent, this philosophical time. And if you look at it in world history, or more specifically, biblical history with the nation of Israel, this is kind of where these folks lay out in the timeline. So the nation of Israel, the Babylonian exile, that's when they taken from Israel, they're carted off into Babylon. That's where Shadrach, Meshach, Abednego, or maybe you know them by their Hebrew names, Hananiah, Mishael, and Azariah, are with Daniel, and his Babylonian name was Belshazzar. So they are in all those stories about the lion's den, the fiery furnace, all that kind of stuff takes place during this Babylonian exile. Then during the Persian domination, this is about the time where, you know, Ezra, right in there. So the stories about the people returning back, or the also Esther's during this time, Persian domination. She's the queen, remember the story of Esther? So that's taking place biblically. At the same time, Socrates is opening, he doesn't actually have a school. The first school is by Plato in 427. He's from 427 to 327 BC, about 100 years lifespan there. And he has the first formal public education institution. Then his student, Aristotle. Now, Plato was an idealist. Plato believed that, and think about scripture for a minute, of how this relates. Plato, as an idealist, believed that things exist because they're a thought that becomes real. Everything that exists has a ultimate reality of which we only see a shadowy version of. When Paul, for example, speaks about that we see through a glass dimly, in other words, we can begin to apprehend spiritual realities, but we can't see it fully. But what happens when we see Christ? We're like him because we can see him as he is. These kind of images, these kind of ideas come from this idealism of Plato. Plato is known for his analogy of the shadows on the wall. He said, pretend your existence was nothing more than you grew up in a cave, and you'd only been in the cave. You'd never been anywhere but the cave. And then behind you is a fire. And so you're staring at this cave wall. Behind you is a fire, and people or other objects are going between you and that fire. What you see on the wall is a shadow of the real thing. You never see the real thing. You just see shadows of it. But everything you see a shadow of, there exists a perfect reality of it somewhere. Just think of it that way. Somewhere other. There is the real. So when you're sitting in a chair, you're not seeing a chair, perfect chairness. You're seeing an image of, a reflection of the perfect chair. But chairs exist, and they exist because of they exist maybe in the mind of the divine, if you think of it that way. See? In creation narrative, how did all creation come to exist? We would say that God spoke it. God said, let there be. Did God speak? Did he use lungs to push air through vocal cords to vibrate to make a sound when God spoke? And most theologians would tell you that what they understand that to mean is God expressed a will and a desire for it to be. And when God expresses a desire for something to be, it is. Because its isness, its beingness, it's called ontological reality. It's ontology. Its realness is based upon God, the divine thought that it does exist. And when God thinks it exists, guess what? It exists. Aristotle was a realist. Aristotle would say, I'm not arguing that there's not these thoughts, but things that we have exist in reality. This chair is more than, it's not just simply a reflection of perfect chairness. It's a chair. It really exists right here, right now. So if you think about it, the people who followed Plato strictly were kind of thinking like, oh, look at that image of the chair. Oh, look at that image of perfect deskiness. And look at over there, that image of perfect chemistry benchness, you know? And Aristotle will come in and say, but it's really a bench. It's really a chair. That's really a desk. And that's the school of idealism, or excuse me, realism as opposed to idealism. And so Aristotle comes along and says the physical thing exists in and of itself. It's really something. And make it personal. You are not just a reflection, simply a reflection of the Imago Dei, the image of God. You are really a person. You're physically really a person. You know? That's where Aristotle comes in and says, okay, the concept is, Plato taught about the concept, but Aristotle says, and there's also reality in the matter itself. It's real. And you see, if matter's not really real, then we're studying things that take up space and contain matter. Then all of chemistry would just be fanciful. It would just be a good notion. But because Aristotle said, no, it's not just a thought, it actually is real at this moment. Now that it's real, we can investigate it. We can learn more about it. And not learn false images of the real thing. We're looking at the real thing when we're looking at something. You see the difference? It's a nuance. We don't think like this because we're so influenced by all these people already. When I see a book, I don't go, oh, look, there's an image of a book. No, I say, this is a book. Is it real? Yeah, how do you know? It's right here. That kind of thinking doesn't fit with idealism. Is it real? Yeah. Why? Because it's in the mind of the divine. See? So, and I'm not the divine one here. This would be God. Appreciate the gesture. So, early attempts to understand matter. It comes down to this idea of continuous and the discontinuous theory of matter. It's a real quick gloss here, but Aristotle proposed, when he was talking about real things, real matter, real stuff, again, my technical term, real stuff, this idea of the continuous theory of matter, he said, and this isn't a quote, this is the idea, that you can take a piece of matter and you can cut it in half, and you can cut it in half, and you can cut it in half. You can keep taking smaller and smaller samples, and you can do this indefinitely. Think about it. If you have a fine enough instrument, this is the concept. We're limited by the precision, let's say. We're limited by the instruments we have. But the theory says, under Aristotle, that if you take something and you keep cutting it in half, that you can do that indefinitely. Because you can always take half of something if you have something. And in the continuous theory of matter, every time you take a portion of that, a smaller portion of that, it is exactly like the larger thing. That every piece is the same as you get smaller and smaller and smaller. It's something like this. Maybe as a kid you had those Play-Doh fun factories, right? Where you stuff the Play-Doh in and you put the star in front of it and you squeeze the handle. And out comes this tube of Play-Doh. It looks like dough coming out of the maker. And it's in the shape of the star, or the half moon, or whatever shape you put in there. That's what comes out. And if you took that piece of Play-Doh and I said, okay, cut it in half. What do you have? You say, I've got Play-Doh. Cut it in half. What do you have? I've got Play-Doh. Cut it in half. What do you have? I've got Play-Doh. Indefinitely, forever, you can continually, perpetually take half and half and half and half and half. And whatever you have in your hand, this theory says it's exactly the same as the larger piece. That matter, a type of matter, is consistently the same. Now, they had different theories about how things held together. They had certain types, like liquids and solids and gases. They felt that they had different shapes to them, so they combined differently, or they had different ways of hooking, like little hooks, kind of like Velcro. They didn't have Velcro back then, but that kind of idea. How do these things stay together? They had a lot of different concepts. But this continuous theory of matter says if I take something and I cut it and I cut it and I cut it, take it smaller and smaller and smaller and smaller samples, that I will never have something other than what I had originally. I will always have Play-Doh. It never breaks down to anything other because I have a chunk of Play-Doh. Again, that's continuous theory. Then this guy comes along named Democritus. Democritus has a slightly different theory, and he proposes this discontinuous theory of matter. So Aristotle, continuous theory of matter. Democritus, discontinuous theory of matter. And he says, again, paraphrase, not a quote, a sample of matter cannot be continuously divided into smaller and smaller parts. He says you can't do that. At some point, you reach a piece that can't be cut down any further. So he's saying as you get smaller and smaller and smaller samples of the same thing, and eventually you get to a place where if you cut it, well, you can't cut it, but if you could, you would have something substantially different than what you started with. At some size of your Play-Doh block, you cut it and you suddenly don't have Play-Doh anymore. You've got something other than Play-Doh. Because Play-Doh is not made up of solid Play-Doh-ness, right? It's made up of other things that appear to be a solid chunk of Play-Doh. Where did he get this idea from? Well, story's told that he was walking along and he saw a beach. I'm sure those folks there in modern attire weren't on the beach when he was there, but you know, you've got this idea, you're walking up and you see, from a distance, you see a beach. And with a continuous theory of matter, that would have been Aristotle's perspective, you'd say, okay, there is the land, which is all made up of land molecules. And then there is the beach. He didn't use the word molecules, but pieces, whatever. So it's all made up of landness. And then I go to the beach, and the beach is all made up of sandness. And then there's the water, and the water is all made up of waterness, right? Let's try to make it simple. So he's saying, okay, so I've got a chunk of land, next to that a chunk of beach, and next to that a chunk of water. But as he got closer, he looked at the sand and said, wait a minute. From a distance, what looks like one big chunk of sandness is actually, when I get down to it, made up of individual grains of sand that don't look the same. From a distance, they look the same. They got this kind of general cast to the sand color. But when you get right next to them, each individual grain is different. So what appears to be the same is actually made up of pieces that are different. Now, which one of these two theories do you believe we agree with and lean towards today? Our current perception of reality. Who do we agree with? Democritus or Aristotle? Democritus. We agree with Democritus. But here's the deal. The world at the time didn't. The world at the time stuck with Aristotle. Why? Well, Aristotle's like the big kid on the block, you know? Aristotle is a student. He is a well-loved and respected philosopher who's the son, or excuse me, is the mentee. He'd been mentored by Plato, a well-respected philosopher who had been mentored by Socrates, a well-loved and beloved philosopher. So guess what? He's got the philosophical lineage. He's got the clout. What he says is until somebody bigger than him comes along to say, no, he's wrong. So even though Democritus was technically, we would say, more right, and we'll see reasons why he's right and reasons why he's wrong later in the course, But the attitude about this information, this material, didn't change for almost, let me see, throw the number out real quickly out of my head, 2,000 years. For almost 2,000 years, the idea was matter is continuous. And when I have a chunk of Play-Doh, and I take half of that, I got Play-Doh, and I take half of that, I got Play-Doh, and I take half of that, I got Play-Doh, to ultimately, I got a microscopic piece of Play-Doh, which if I had the right tools, I could cut in half for an infinite number of times and always have Play-Doh. It's not until the 1700s we get to Lavoisier, Antoine Lavoisier. So if you want to know how to say it, there you go. Antoine Lavoisier. Here's a Lavoisier. We probably have a charming picture of him. There we go. There's Lavoisier. So Lavoisier comes up with this idea called the law of mass conservation. You probably know it as the law of conservation of mass, whichever. Here's the idea. Mass is conserved. Now what's mass? Stuff, right? It's this idea that matter cannot be created or destroyed. It can only change forms. So what Lavoisier is saying is when we do an experiment or when we're experiencing life and we see what we're going to come to know as a reaction, when we see things interacting with one another, at this point they're not saying, well, chemical interactions are mostly based upon the valence shell electrons and their interaction and whether it's a metal or a non-metal and whether it's going to be a covalent or ionic bond and all this kind of stuff. This all comes later. This is like the very elementary kind of things. And Lavoisier says, you know what? I got this crazy idea that I can't make or destroy anything. All I can do is change what it looks like. And there'll be some certain times in this course where I'll use this analogy, but I'll say, for example, when we do stoichiometry, certain things, frankly, you don't have the authority to do that. That authority rests with God. God creates out of nothing, called ex nihilo, right? He creates out of nothing. And God, we would argue, has the ability to destroy, to take something and turn it into nothing, because he's the one who can take nothing and turn it into something. Creatures, which is everything other than God, all we've been given the authority to do is take God's Legos and put them in different shapes. We can't make anything out of nothing. We can't take something and make it into nothing. All we can do is mess with it and shape it and turn it around and mold it. Okay? So this idea of conservation of mass says if I have some things inside of a closed container, if you think of it as an aquarium with a solid lid, some space where nothing can come in and nothing can come out, and I have this closed container, so whatever's inside is captured inside, if I am able to make them react, if I'm able to get them to do something and change their form, that I haven't lost anything and I haven't gained anything. I've simply molded it, changed it, to look like something else, to take up a different volume, to have a different color, to be in a different phase. But I haven't really made or destroyed anything. I've just changed the way it looks. I've changed its appearance. And since I haven't lost or gained anything, the amount of stuff that I have hasn't changed, then the mass of what I have hasn't changed. See, in order for me to have more stuff, I'd have to create it, or I'd have to allow stuff from the outside in. And I can't have less mass, because if I have less mass, then I've destroyed it, or my container has a hole in it and something's gone out. Scientists at this point didn't have the ability to observe everything, so they tended to think of matter as disappearing. They tended to think, okay, I've got this thing and I've got this thing, and I bring them together, something happens, and it looks like I have less. And we sometimes get tricked by that, don't we? Because I can't see it, we think it's not there. Go back to our discussion on the very first day of class. Air, it's a gas. Because it's a gas we can't see, we tend to think it's not there, but it's there, right? So if I have two solids and I make a reaction, and those two solids create a solid and a gas, some of my matter has changed phase and I can no longer see it. So an uncritical scientist might say, oh, you've destroyed matter, you've lost something. Well, no, I haven't lost it. I just can't see it anymore, so it might appear like I've lost it. But it's still there. It's now in a form that I can't see. So if we can capture all the material and all the products, the mass remains the same. In this case, we're going to talk about combustion. We went camping this past weekend. We had a couple campfires, and it seems like you have a campfire, you take wood, and when you have the combustion of wood, you've got wood and you've got oxygen. Now, the fire triangle is what? Wood, oxygen, and heat, or energy, right? If you have fuel, if you have oxygen, and you have heat, it'll form a reaction. We call that combustion. It burns. Burning is a reaction. Something's happening. Something's being converted. So you start with wood and oxygen. You add heat energy to that. And when you're done, what do you have left? At the end of your fire, what's left? Well, you've got ashes, right? The campfire ring had this piece of wood in it at the beginning, but by the end, it's just a pile of ash. Now, if you look at that and say, I had a big log, and I converted a big log into a little tiny pile of ashes, it looks like you've lost matter. It looks like you've converted a lot of something into very little of something. But we're more savvy than that, because we know we burn. We not only produce the ash, which is the physical material solids that are left over, but also in that burning, we release water vapor. Water vapor comes off as a white smoke. It's that steam that comes out of the wood. Wood is, like us, has a lot of water in it. And so when you heat up the wood to burn it, the water in the wood evaporates and turns into steam. So the mass of the ashes that are left behind, plus the mass of the water vapor, the water that turned into steam and now left the campsite, and the carbon dioxide, which is another product of combustion, that gas has left the site. This argument would say if I have a piece of wood and I put enough oxygen in a container and I add the energy to start the fire and I keep everything inside, if that wood burns inside of a closed container, when I'm done, I will not have made or destroyed anything. All of the matter that was in that container before the fire is still in the container after the fire. It'll look very different, but you haven't gained or lost anything. And because you haven't gained or lost anything, the mass is the same. So if you take the mass before the reaction and the mass after the reaction, they should be the same. So example 2.1 in your book, that's on page 49. It says that a chemist notices that when given enough energy, a white powder changes into two different substances, tin and oxygen. What might that look like up here? Well, we're going to start with this idea, and you guys haven't seen a reaction arrow yet. But here's what a reaction arrow says, what it communicates. This reaction arrow gives us a direction in time, and it says, hey, I've got a certain reactants. The reactants are those things that are going to react. Pretty complicated, right? And the reactants, when they react, are going to produce products. So vocabulary should be pretty easy here. The reactants, when they react, produce products. And we've learned that conservation of mass says whatever the mass I have of my reactants has to be equal to the mass of my products. Because I'm not gaining or losing matter, I'm just changing its form. I'm changing the way it appears. We're changing several different things, okay? But I'm not creating something out of nothing, and I'm not destroying anything. So my mass stays the same because I haven't created or destroyed matter. So in this case here, we've got a white powder, and that white powder is my reactant. It becomes tin and oxygen. Later on, we won't use tin. We'll use, over from the periodic table, the symbol SN for tin. Looks like sin, but it's tin, SN. And also oxygen. It's O, more specifically O2. Don't worry about that for right now. Right now, the concept is I've got something, it undergoes a reaction, and it produces something. My white powder undergoes a reaction, and it produces tin and oxygen. This becomes this. Okay. The chemist watches 151 grams of powder undergo the change. And they collect the tin that was formed, and its mass is 119 grams. But unfortunately, he couldn't collect the oxygen. In other words, he burned it, but the oxygen just floated away, took off. He didn't have a closed container. So, using the law of mass conservation, determine how much oxygen was made. Now, because my white powder becomes my tin and oxygen, my white powder are my reactants, and the mass of the reactants equals the mass of the products, I say, well, whatever the mass of the white powder was, if white powder becomes and only becomes tin and oxygen, then the mass of my powder has to equal the mass of the tin and the mass of the oxygen combined. Anybody struggling with this? Does this make sense? That the reactants become the products. The mass of the reactants has to equal the mass of the products because I haven't made or destroyed anything. I've just changed its form. In this case, the form of white powder becomes the form of tin and the form of oxygen. Okay, so I need to solve for what? Use the law of mass conservation to determine how much oxygen was made. I'm going to rearrange this formula to solve for mass of oxygen, because that's what I'm asked for. How do I do that? Pretend that this is A equals B plus C, and I'm solving for C. How would I get C alone? Do you see that I'm asked to solve for the mass of oxygen? Okay. What is the mass of oxygen equal to, given that formula? Again, imagine if you would in your mind, if it said A equals B plus C, what would you do to solve for C?
When you just subtract like mass.
You'd subtract B, right? Yeah, good. So I'm trying to get mass of oxygen all by itself. I can do that by subtracting the mass of tin from both sides. And when I subtract the mass of tin, I'm left with mass of the powder minus the mass of tin is equal to the mass of oxygen. Okay. So again, mass of the powder, that's how much of the reactants I have. That mass is going to equal to the amount of tin and the amount of oxygen that I produce. I've been given the mass of the powder, and I've been given the mass of the tin, and I've been asked for the mass of the oxygen. So I rearrange the formula to solve for what I've been asked for. My two knowns, mass of powder, mass of tin, and the difference is the unknown, the mass of oxygen. So in this problem, they gave us some numbers. We plug those in. I just take this formula and flip it around. I wrote it the other way. Mass of oxygen equals what? The mass of the powder. Well, the mass of the powder was given as 151 grams. And the mass of the tin was given as 119 grams. I take the difference there, and I get 32 grams. So the mass of the oxygen was 32 grams. If I take 119 and 32, I have 151. What's that saying? The mass of the white powder is equal to the mass of the products of the reaction. The mass of the white powder is equal to the mass of the tin plus the mass of the oxygen. If I have one of those two, I can solve for the other one. If I have two of any of those three. Given this, if I didn't know the original mass of the powder, but I said it produced 119 grams of tin and 32 grams of oxygen, well, you should be able to come back and say, well, then you have 151 grams of powder. Why? Same mass. Whatever was in the reactants, that mass has to equal the mass of the products, all of the products. Not just the physical products, but the mass of any vapor that was given off, any other gases that were given off, any liquid that's produced, any solid that's produced, the mass of the whole thing. Because those are building blocks that were part of the reactants. So they are what are used to create the products. Because we're not creating out of nothing, and we can't destroy anything. All we can do is rearrange it. In this case, we rearranged white powder into tin and oxygen. Go ahead on your own. Give on your own 2.1 a shot. I'll give you a head start, and then in a few moments, we'll walk through this together. Okay. A compound is decomposed into its constituent elements of. What does that mean? Decomposes into. If I start with the same thing I did before, the reactants and products, a decomposition reaction, and we'll get into this later, but a decomposition reaction means you have something and it produces pieces that make it up, smaller pieces. Okay? It decomposes means to break apart. It's not like in biology where decomposition is something gooey and slimy. Okay? Here in chemistry, decomposition means I have a big structure, and when I decompose it, I break it up into smaller structures. So the larger structure here, whatever it is, decomposes into carbon, nitrogen, and hydrogen. And it gives you the masses and asks what was the mass of the compound before it decomposed. So they're asking you for the mass of the reactants, and they give you the mass of all the products. So the reactants produces products is a very general basic equation that applies to everything, all the reactions that we do. We'll build on more and more complicated reaction equations as we go. So the mass of the reactants is equal to the mass of the products. That is the law of mass conservation. Okay? That the mass of the reactants is equal to the mass of the products. The products in this case, you're given carbon, nitrogen, and hydrogen. Now don't worry about the notation, but that the C, the N2, and the H2, those are the symbols for carbon, nitrogen, and hydrogen. We'll get into why those are the symbols later on. I just needed to make it smaller to fit on that one line. So just trust me, since the products of reaction are carbon, nitrogen, hydrogen, well, the mass of the products is the mass of the carbon plus the mass of the nitrogen plus the mass of the hydrogen. Those three things are the product. So the mass of my product is going to be the mass of each of the products added together. That mass of the products are given as 12.0 grams of carbon, 14.0 grams of nitrogen, and 3.0 grams of hydrogen. We're using addition. Therefore, our answer can only be as precise as the least precise, but they're all to the 10th place, right? So our answer is going to be to the 10th place, and that is 29.0 grams. So I have a reaction, and everything that was in the reaction that reacts has a mass of 29 grams. That's the products. The sum of the masses of all of my products is 29 grams. So how much stuff reacted to produce 29 grams of stuff? If 29 grams of stuff are produced, then 29 grams of stuff was used to produce it. That's the key for the law of mass conservation. The mass of what I end up with has got to be equal to the mass of what I started with. Otherwise, I'm playing God and creating something out of nothing, or I'm playing God and turning something into nothing, or I have a bad system and while I'm doing the reaction, stuff is escaping and stuff is entering. It's not a closed system. It's an open system. But in chemistry, if we have a closed system, meaning we've got everything captured and we run the reaction in that captured space, the mass of everything that reacts has to equal the mass of everything that's produced. In this case, 29 grams of carbon, nitrogen, and hydrogen were produced, added together. The 12 grams of carbon, 14 grams of nitrogen, and 3 grams of hydrogen, which is 29 grams total, that comes from 29 grams of something else. It didn't come from 35 grams of something else. It didn't come from 2 grams of something else. It has to come from the same amount of stuff. Because again, all we've done, and I keep going back to this, but I'll probably bring them in. I use Duplos and not Legos in class because it really gets down to the building blocks of stuff. I've got 29 grams of building blocks. Okay, let's just make it that, Duplo, okay? Remember, you played with Duplo blocks? Let's say that you have 29 grams of Duplos. And you take the 29 grams of Duplos, which are made into one big chunk, one big wall, right? My son liked to do that, build walls. So let's say we have a big wall that has 29 grams of Duplos in it. If I take that wall and I break it down into a bunch of little pyramids of 3, okay? I haven't added any Duplos. I haven't lost any Duplos. All I've done is rearrange the Duplos. When I'm done, how many grams of Duplos do I have? 29. Because I haven't lost any Duplos and I haven't added any Duplos, all I've done is I've rearranged the Duplos that I have, or Legos or whatever other toy you want to talk about, right? I've just rearranged them, but I haven't lost any, I haven't gained any, so how much stuff do I have? I got the same amount of stuff. That is the concept of conservation of mass. And it is a fundamental concept that you're going to, again, use over and over and over. It's got to just be part of your thinking. How much stuff do you need in order to produce this much stuff? Well, I need the same mass. If I know the reaction, and if I know how much stuff I need to produce in terms of mass, then I need that much mass of the stuff that produces it. Okay? That is the whole concept of conservation of mass. Starting tomorrow, we're going to get into the elements, the building blocks of matter. So we'll pick up on page 50 and the discussion on elements tomorrow. Any questions for me on the law of mass conservation, the principle? How successful were you at working out on your own 2-1? Okay? Okay. It should be pretty straightforward, but that's not to discourage you. That's to encourage you that it's not that difficult. Just apply yourself. The answer, the working it of 2-1, it's in the book. So if you need to review the answers that are in the book, please do that. And again, the basic principle again is that however much stuff you have before you react it, before you change its form, when you're done changing its form, you will have the same amount of stuff. It gets confusing, like with Lavoisier's counterparts when they burn something, because like the analogy I used at the campfire, you've got a big piece of wood that becomes a very small pile of ash. It looks like you've lost stuff. You've lost stuff only because you let it float away in the smoke. You let it float away in gases. If you had been able to capture all of that, you would have found that the mass of the wood is equal to the mass of the ashes plus the mass of the oxygen plus the mass of the carbon dioxide plus the mass of the water vapor. That all equals the mass of the wood plus the mass of the oxygen that was used to burn it. You haven't lost or gained anything. You've just rearranged it into, you've taken oxygen and wood and you've changed it into ash and water vapor and carbon dioxide.